This will be the first of 3 lectures on habitat use patterns in animals. Habitat selection is a critical issue in conservation biology because habitat loss or degradation is the most important or key cause of population declines in most species that are facing population challenges. For example, least terns are having significant issues with loss of habitat. Snowy plovers, another example of a shorebird in which their beach nesting habitat is critically endangered. So there are 2 basic patterns of selection and use of habitats that we're going to be covering. We'll first talk about exploitation competition, which is non-territorial use of habitat. Then we'll move on to talking about territoriality or resource defense competition. So an example of the first, exploitation, another term for it is scramble competition, is seen in grazing ungulates. Many territorial species of animals exist. It's very common in passerine birds like red-winged blackbird. So you can see a male here singing and displaying to potential rival males so that it can defend its territory boundaries to have exclusive use of the resources of that territory. When we examine habitat use pattern in animals, we're oftentimes examining it from the perspective of the economic use. So in a similar way that we talked about optimal foraging, we can talk about optimal behaviors associated with habitat use. We're going to assume that individuals are trying to maximize benefits and reduce costs. And in some cases, it may be to the advantage of individuals to simply use resources. The resource may not be valuable enough to defend, and the cost of defense could be too high. In other cases, it may be important to defend the resource. Cost of defense may be relatively low given the huge benefit of exclusive use of a resource in a territory. We'll also talk about natal dispersal options and other dispersal options in animals. And finally, in this section, we will discuss migration behavior. So let's first talk about exploitation or scramble competition. Again, exploitation competition, and another term for it is scramble competition, is a situation in which there is no territorial defense of a resource. A key concept to understanding exploitation competition is the ideal free distribution. This is models of expectations of how competitors should sort among potential resource patches when using a habitat. There are certain assumptions required for the ideal free distribution to be met. One of these is that all individuals obtain the same net gains associated with whatever habitat they're using. It assumes that there's no territoriality or despotic behavior. Individuals are free to go wherever they want to go among multiple potential habitat patches. And it assumes that individuals have some base knowledge of the resource distributions, and they use this knowledge to move among patches so that they can maximize their net gains. In other words, they have to have some potential to behave optimally. Okay, so let's talk about an example of the ideal free distribution. A very simple example where you just have 2 habitat patches. One is a resource-rich patch. One is a relatively resource-poor patch. Individuals are free to move among these habitats, so there's no territoriality, no despotic behavior. So obviously in this situation, the first individual is going to go to the rich patch. Maybe the second individual will go to the rich patch as well. So here we have the example. The darker coloration is indicating a richer resource patch. First individual is going to go there. Maybe the second individual is going to go there. But what is this next individual going to go do? They may actually attempt to go to the resource-rich patch, but find because of the competition for the resources there, the previous individuals may have depleted the resources at this patch, that it actually may be better to go to the relatively poor resource patch. But again, this is only going to be true if the resource gains at the rich patch are now below those of the poor patch. In other words, the poor patch now is the better choice for this individual. So individuals will choose among patches depending on the level of competition and resource depletion at each patch due to previous use of patch. So at the time that any individual arrives, the profitability of each of the patches that are involved will be equivalent. And here's a model that demonstrates this idea. So on the x-axis we have the number of competitors, and there are different numbers of competitors that can be in a rich patch or a relatively poor patch, and there will be different rewards per individual at each of these. So the blue line indicating the rich habitat obviously is to the right of the poor one, indicating that for a set number of competitors you're going to be better in the rich patch than the poor patch. But the idea here is that once you end up accumulating a large number of individuals in the rich patch, that will be associated with a certain amount of rewards per individual. And that if you add individuals to this rich patch, and that might put them at this location, they would actually be better off not going to the rich patch, but instead going to the poor habitat patch, where they would be able to get these rewards. And so individuals were going to be bouncing back and forth with subsequent individuals entering the population into these habitat patches. They're going to be bouncing back and forth between the rich habitat, and then a new individual will come into the poor habitat, and then a new individual will go to the rich habitat. As long as all of the individuals at any given time are experiencing the same rewards, regardless of the complete quality of the habitat. Because of competition and resource depletion, they're actually balancing out so that everybody has the net gains as long as the appropriate number of competitors are in each habitat type. Now, here's an everyday example of this that everybody should be able to identify. When you choose a line to check out at the supermarket, you are following the predictions of the ideal free distribution. In this case, what you're trying to minimize is the amount of time you spend in the line. And so you will use your information to try to pick the appropriate line. But everybody else is using the same information, and so they will be assorting themselves into different lines so that if you look, when you get in line at the same time as someone else gets into another line, y'all should finish at about the same time. Now, that's assuming all of the assumptions of the resource of the ideal free distribution model are met. And pretty much there's not any despotic behavior, so individuals are not elbowing each other to keep from joining lines, so we can pretty much assume that one is being met. But maybe everybody doesn't get out at the same time, and what may be violated here is the amount of information you have. Okay, you can't always tell each checker how fast they are, so your knowledge of kind of patch value may be limited. Some people are faster at checking out. Somebody that's writing a check is going to take longer than someone that's using a credit card typically. So that's the one issue of the assumption of the ideal free distribution model that's most likely to be violated. Here's a study that demonstrated the ideal free distribution model with sticklebacks feeding on crustacean prey, Daphnia. What they did is they dropped prey at two different rates at opposite ends of a tank. One end of the tank had about a double the drop rate as the other. And basically what they demonstrate is that the fish distributed themselves as expected. Proportionally fewer individuals were at the low distribution rate, and individuals at the high distribution rate there were many more individuals there. But individuals moved back and forth with changes in prey drop rate. And they did so in very predictable ways to meet certain expectations. So some of the predictions that were verified, individuals at both ends of the tank had equal intake rate. Numerical prediction was also met. Individual per prey ratio was equal at the different ends, and of course that's obviously related to the equal intake prediction rate. The figure here shows you how they made the changes during the experiment. So time is on the x-axis, and at point X, they had end that's labeled end A being the low resource rate. And they had a very low rate of Daphnia being dropped there, and they basically settled into 2 fish at that end of the tank after they were able to figure out the distribution, the fish were. But at point Y, you see that's when they switched the prey rate on opposite ends, and they doubled the prey rate at end A, and end B now became the low rate. And what you see is after a few minutes of confusion, the fish pretty quickly realized, no, we have to go to the other end. More fish should go to the other end to maintain our feeding rate. And so end A became had twice as many fish because there was twice as much prey that was being delivered. So indicating that fish were able to move back and forth, there was no despotic behavior, and that they were informed about the rate of droppage at both ends. So they were able to make an optimal decision. When honeybee colonies become too large, they'll actually split in half, where half of the individuals will leave the hive with a new queen, and they'll gather on a nearby branch where they will use that as an information center, and individuals will fly in different directions searching for a new permanent hive location. Here's a figure that shows you from the 19th of June through the 21st of June how individuals start going off in all different directions early on, and then they all come back and are indicating consensus on a specific direction, in this case south, as the location where the new hive is going to be located. Well, what kind of decision making are they using when deciding what would be a good hive location versus a suboptimal hive location? Well, given equal quality of hives themselves, they pick the one that's most distant from the daughter colony from which they have branched off. What this does is it reduces competition between hives. So it's a way that they can guarantee that they have equal resource gain without competing with each other, which is one of the predictions that you would have from the ideal free distribution. So in review, understanding habitat use in animals is very important in species that are under conservation concern. We talked about exploitation or scramble competition as one way that organisms can utilize the resources in an area. And in this situation, the distribution of individuals fits what we call the ideal free distribution, where individuals know the resource distribution pattern among a series of habitat patches. Individuals are free to move among these patches in a way such that all individuals receive equal resource gains.